The first thing that I want to talk about today is the concept of a time constant. So, in the last lecture, a first order RL circuit where we had some current source IS. I want this thing to go away. In parallel with the resistance RS. And then we had a switch that was opening at t is equal to 0. Here we have a resistor R. And here we have some inductance L. And let's call the current through the inductor IL of t, the current through the resistor IR of t, and the voltage drop over both V of t. We observed and showed that literally all three of these symbols, or signals, excuse me, obeyed the following relationship, where the voltage or current was equal to whatever value the voltage or current had at t is equal to 0 minus for all time less than 0 minus, so all points in time before the switch changed. And then it had a value of y of 0 plus e to the negative r over L multiplied by time for t greater than or equal to 0 plus, or all points in time after which this switch had changed states. Okay. So engineers have given that rate of decay for this system a special name called a time constant. All right. Where a time constant tau is defined as such. Y of tau is equal to y at 0 plus e to the minus 1. So effectively, a time constant is just a measure of how long it takes for the signal to decay to a very specific value. Okay. So if we were to plot, say, an inductor current as a function of time at exactly one time constant, we should observe, if this is its initial value, decays like so, that at exactly one time constant, its value is 0.368 of whatever it was. If we call this I naught, this guy will be I naught. So what this means is that in one time constant, the signal decays to 36.8% of its initial value. And we can tell this because this is simply e to the negative 1. E to the negative 1 is 0.368. Well, in two time constants, we will have e to the negative 2, which is 13.5%. And 3 time constants, which is simply e to the negative 3. We have a decrease down to 4.98%. And 4 time constants, which is just e to the minus 4. Our signal is decayed down to 1.83%. Pardon me. And finally, in 5 time constants, our signal has decayed down to 0.67%. Okay. So in 5 time constants, our signal has gone from full strength, whatever that happened to be, down to less than 1% of its original value. Engineers treat 5 time constants as effectively infinity, because at this point, our inductor has pretty much fully discharged to all noticeable or measurable degrees, okay? Excuse me. So we could rewrite our generic equation here in terms of our time constant, which actually, before we even do that, based on our definition here, what should our time constant be for an RL circuit? It's not R over L, right? It's L over R, exactly right. So when T is equal to L over R, our exponential of e to the minus R over L times L over R goes to e to the minus 1, which tells us that we are at exactly 1 time constant. So for an RL circuit, we would have y at 0 minus, t less than 0 minus, and then y at 0 plus to the negative t over tau for t greater than or equal to 0 plus, where tau is defined to be L over R. I'm intentionally introducing this more generalized case, which uses a time constant instead of the specific L over R relationship, because we are going to find out in just a couple of minutes when we're dealing with first order RC circuits, that's going to have a very similar response. And so we can actually apply the same set of steps, where one of our steps will now just be to determine the time constant of the system and treat any first order circuit in the exact same way, so that we don't have to change the style of our analysis or anything like that. We'll follow the exact same steps. So before we move along to our capacitor circuit analysis, does anybody have any questions regarding the concept of a time constant? A time constant for electrical engineers is effectively the same thing as, or not the same thing, but similar to the concept of half-lives for chemists. Just telling us by how much our signal decays for a specific rate of decay. Okay. All right. So let's talk about the natural response of RC . All right. So if we have the following circuit, where we have some voltage source Vs in series with some resistance Rs, and then we have a switch that's going to open at t is equal to 0. And that switch is connected to a resistor in parallel with a capacitor, like so. Let's call this voltage Vc of t. It is the voltage drop over the resistor as well, but let's just call it Vc of t for right now. Excuse me. Let's call this current Ic of t, and this resistor IR of t. So if we were to analyze this circuit at t is equal to 0 minus, it would look something like this. Excuse me, this should be at 0 minus. So I'm going to ask you guys what I hope to be a fairly simple question. Is there a voltage drop across the capacitor in this instance? So the capacitor is in parallel with the resistor that I've labeled R. Is there a voltage drop over the resistor that I've labeled R? Sure, absolutely. We can determine what it is using voltage division very trivially, right? We know that this voltage here, let's just call it VR, which is identical to Vc at 0 minus, would simply be Vs multiplied by R divided by R plus Rs using voltage division. Everybody okay with that? So since our capacitor has some voltage drop over it, it must have some energy stored in it, right? Excuse me. At t greater than 0 plus, or actually t is equal to 0 plus, the instant after the switch has changed states, that capacitor voltage doesn't change, and so the capacitor has to keep that amount of stored energy. And then as time progresses, it will gradually transfer its energy to the resistor, which is effectively the exact same thing that we saw with our inductor circuits on Wednesday, right? So for t greater than or equal to 0 plus, the situation we have is this. We have a voltage source connected to some resistor Rs, and then we have an open circuit over here. And then on the right-hand side, we have some resistor R, some capacitance C, and then we have some voltage Vc of t, our current Ic of t, and the current IR of t, and we know that Vc at 0 minus had to be Vc at 0 plus, which had a value of Vs over R divided by R plus Rs. So to understand how it behaves for all time after our switch opens, we're going to have to set up another differential equation and solve it again, okay? So we could say that IR of t plus IC of t is equal to 0 by applying Kirchhoff's current law at our top node, top right-hand node. We can express both of those currents in terms of that common voltage, V of C. So that would be 1 over R times V of C plus C dV by dt is equal to 0. And we have a homogeneous first order differential equation, just like we had with our RL or inductor resistor circuit. So I'm going to use the same guess and say that I believe that VC of t here will be of the form AE to the ST. And from this, I get A times, actually, I'll do it in multiple steps so I don't mess it up. 1 over R AE to the ST plus SC AE to the ST is equal to 0, or A multiplied by 1 over R plus SC e to the ST is equal to 0, which will only be true when S has a very specific value. S must equal -1 over RC. And from this, we can see that our guess becomes AE to the -t divided by RC. We determine A, just as we did before, by looking at the value of that signal at t is equal to 0 plus. And so finally, we would have VC at 0 plus e to the -t divided by RC as the response of our capacitor voltage for all t greater than 0 plus. So it's effectively the exact same equation that we had previously, except that our time constant has changed, right? For an RL circuit, we saw that we had a time constant of tau was equal to L over R. For this RC circuit, excuse me, goodness, we see that we have a time constant of just R times C. And now we have a means by which we can analyze RC circuits exactly like we analyzed RL circuits on Wednesday. It's a simple 4-step process. We analyze the circuit at t is equal to 0 minus, analyze the circuit at t is equal to 0 plus, determine our time constant, and then plug those values into our generic equation, where the generic equation that we developed for our inductor obviously should behave for our capacitor circuits as well. So in general, we will analyze the circuit at t is equal to 0 minus, Analyze the circuit at t is equal to 0 plus. Determine the time constant where tau is equal to L over R for RC circuits. Tau is equal to R times C for RC circuits. And then step 4. Plug the results of step 1 through 3 into our generic equation. So let's analyze an RC circuit. Find one here somewhere. All right, looks like I'm going to make one up. So let's say that we have an 8-volt source. A switch that opens at t is equal to 0. A 5-ohm resistor. A 10-ohm resistor. And then a 0.5 millifarad capacitor. And we want to know this voltage, DC of t. And we want to know this voltage, VR of t. So our first step is to analyze our circuit at t is equal to 0 minus. At t is equal to 0 minus, we are at DC steady state, which means our capacitor will look like an open circuit. So I'm going to go ahead and draw this over here. Here's our 10-ohm resistor. Here's our 5-ohm resistor over which there is a voltage drop VR at 0 minus. And then should my switch here be a short circuit or an open circuit? Short circuit. All right, so I need to determine excuse me, gosh, VR at 0 minus and VC at 0 minus. Anybody have any thoughts? Go ahead, Carter. 8 for VR. So the 5-ohm resistor is directly in parallel with the 8-volt source. So that seems like a very reasonable thing. Anybody who isn't Carter, care to take a crack? Excuse me, here to take a crack at VC. Just let somebody else have a chance. All right, let me help you guys along here. How much current flows through the 10-ohm resistor? None, because it's not connected. So if there's no current flowing through the 10-ohm resistor, There's no voltage drop over the 10 ohm resistor, which means the voltage drop over the capacitor is just the voltage drop over the 5 ohm resistor, which we already know to be 8 volts. So VC has to be 8 volts as well. Everybody okay with that? If anybody has a question, I'd be happy to answer it. All right. Are we satisfied with the circuit analysis that we've done here at t is equal to 0 minus? I think so. All right, so now we'll move along to t is equal to 0 plus. So at t is equal to 0 plus, we're going to have our 8 volt source, but now our switch is open circuited. Here's our 5 ohm resistor. Here's VR at 0 plus. Here's our 10 ohm resistor. And at exactly t is equal to 0 plus, since the capacitor voltage cannot change abruptly, we know that if it was 8 volts at 0 minus, it must continue being 8 volts at 0 plus. So I'm going to represent this capacitor by an 8 volt source. So it'll have the same voltage as VC at 0 minus and the same polarity as VC at 0 minus, telling me that it did not change. So we know we need to find VR at 0 minus, but we know that VC at 0 minus has to be 8 volts because the voltage drop across the capacitor cannot change abruptly. Thank you. Both of those should be 0 plus. Thank you. So, McKinley, how would I go about figuring out VR at 0 plus? Any thoughts? It isn't. Right, so for it to be in parallel, let's identify our nodes here real quick. So here's a node. Here's a node. Here's a node. For it to be, I guess technically speaking, I'll go ahead and do this one over here as well. So for it to be in parallel with the 8 volt source on the right, while they do share the pink node at the bottom, the orange node and the green node aren't the same node, so they can't be in parallel. And it's not in parallel with the 8 volt source on the left because the orange node and the red node aren't the same node. Take another crack at it. Well, there's only one mesh because there's only one closed current carrying path, so I feel like that's kind of overkill, but we could absolutely do that. So let me, not my intention to pick on you here. Let me make this clear. But if I gave you this circuit, could you solve it? It's the exact same thing as the one above. How would you solve the one on the bottom without all the extra crap that isn't really doing anything? Sure, you could do Ohm's law to find the current flowing through the 5 ohm resistor and then multiply it by 5 ohm. Absolutely. We could also do voltage division. We could write a KVL loop around it, which is kind of what you suggested when we were doing mesh. My point here is to let you guys think about things like, I understand that there's a lot of stuff that looks like is happening in that top representation where I've colored in the notes. But the only things that are actually doing anything here are those 3 elements. And analyzing that circuit hopefully shouldn't be that difficult. So let's use the suggestion of Ohm's law to figure out what that guy is, right? So we're going to have 8 volts divided by 5 ohms plus 10 ohms. That's the current multiplied by 5 ohms. And that should just be, holy hell, what the hell just happened? Eight-thirds of a volt. My mental math is correct, which I believe it to be. Get the same result, voltage division, or any other way we take a crack at it. Okay. So are we satisfied with our analysis at t is equal to 0 plus? We have our 2 quantities of interest. All right. So our third step here is to determine our time constant, where tau is equal to REQ times CEQ, right? So since there's only a single capacitor in our circuit, determining C is fairly trivial here, right? C is just half a millifarad, which is, I believe, what I used. Yes. Determining R should be fairly straightforward, but again, I want to burn it into you guys' brain how to do it correctly. So I'm going to draw my circuit during the transient condition. So effectively, it's exactly what it is at t is equal to 0 plus. Here's my 8-volt source. Open circuit. Here's my 5 ohm resistor. Here's my 10 ohm resistor. Here's my capacitor. I'm trying to find the equivalent resistance with respect to the capacitor. So that means I take the capacitor out and I look in to the terminals where the capacitor was. But because this is a Thevenin equivalent voltage, or excuse me, resistance, we have to be looking at a dead network. So what is the equivalent resistance we see? Brett, got an idea? Yeah, there's 2 resistors in series. So 5 plus 10 is 15. And from this, tau is 15 ohms times 0.5 millifarads. Is 3/400 seconds. Is everybody okay with the analysis here we did to determine our time constant? Nobody seems to be raising any sort of objection. So let's move along. Our last step is now plug in the results into our generic equation. So into generic equation. So as a reminder, our generic equation is y of t is equal to y at 0 minus, for t less than 0 minus, y at 0 plus e to the negative t over tau, for t greater than or equal to 0 plus. Went slightly too far. So we're looking for VC and VR. So VC at 0 minus was 8 volts. So we just plug that in. VC at 0 plus was 8 volts. So we're going to have 8 to the negative. So negative T over tau is going to look like negative 400 over 3 multiplied by T. So effectively, all I did was just flip over my fraction for tau, because T over tau is the same as T times tau to the minus first power. Volts. T greater than or equal to 0 plus. And I can do something similar here for my resistor voltage. 8 volts for T less than 0 minus. 8/3 e to the minus 400 over 3 T volts for T greater than or equal to 0 plus. Any questions regarding our analysis here? All right. So since nobody's raising any questions or anything like that, I would like to now talk about driven RL and RC circuits. So effectively, all that means is now we're going to talk about what happens if an independent source is left in the circuit at T is equal to infinity. Okay. So I'm talking about something like this, where we have some voltage source Vs, we have some resistance Rs, and we have a switch. Now we say that our switch closes. We're not going to go through a big formal derivation for this because we actually already have a very good understanding of 95% of it. All right. So the calculus that we did about, I guess, 15 to 20 minutes ago at this point effectively told us how a capacitor discharges over time. And the work that we did on Wednesday tells us how an inductor effectively discharges or releases its energy over time. The only difference between this circuit and the circuit that we analyzed earlier is that we're starting from a position of there was no energy, and we're ending up at a position where energy is being stored, right? Obviously, for T less than 0, the resistor R and the capacitor C have no voltage drop across them or current flowing through them because they weren't connected to anything, which means there was no energy stored in the system. When the switch closes, the capacitor is going to slowly start to charge, and that rate of charging is dependent on the time constant of this new circuit. And then at a very long time, T is equal to infinity, let's call it, the capacitor voltage will settle to its final value, which in this case, so let's call this guy the capacitor voltage. So at T is equal to infinity, we're going to have this circuit. RS R and here is VC at infinity, which using voltage division would just be VS times R over R plus RS. So this T is equal to infinity analysis is what's called the forced response of the system, because we are forcing our energy storage element, in this case, a capacitor, or the voltage drop across the capacitor, to have a fixed value at T is equal to infinity. Well, the total response of this circuit is simply the sum of the natural response, which is what we were talking about earlier, plus the forced response. So, generically speaking, let's start from a point where we believe the system behavior is as such, okay? Let's start with our natural response. Y at 0 minus for T less than 0 minus. And I'm going to leave myself some room here. Y at 0 plus e to the minus T over tau. For T greater than or equal to 0 plus. Okay? So we know that at T is equal to infinity, a long time in the future, or a long time after our switch has changed states, our capacitor voltage should settle to some non-zero number, right? That's what our analysis at T is equal to infinity tells us. So what I'm going to suggest that we do is we add a term here plus y at infinity. All right. So let's think about what the repercussions of that change are. What does our exponential bit do as time increases? Does it get bigger or does it get smaller? Smaller, okay? So at T is equal to infinity, the exponential part is effectively 0, and we just see that constant DC value, which is exactly what we would expect after our transient condition is stopped, because we have to be at DC steady state again. Now, one small problem that we have here is that this constant term of y at infinity is always added into our response, okay? So it's added even for small values of T. To correct that, we simply subtract it right here. This will force our capacitor voltage, in this case, to be a continuous function, okay? Because if we didn't do it, using just kind of a quick analysis here, okay, we can look at this thing. What is VC at 0 minus? Literally anyone. The switch is open at 0 minus. It's 0. The capacitor isn't connected to anything, so it should be fairly straightforward to see that VC at 0 minus is 0 volts. What's VC at 0 plus? David. Still will be 0. Absolutely right. The capacitor voltage cannot change instantaneously. So if we didn't have this term right here, we would see that VC of T would look like 0 for t less than 0 minus, and then 0 e to the negative t over tau plus dc at infinity for t greater than or equal to 0 plus. But this is obviously a mistake because the capacitor voltage can't change abruptly. And we're saying that at t is equal to 0 minus, it's 0, and at t is equal to 0 plus, it's whatever value it had at infinity. That's why we absolutely have to remember to include this subtraction term. Okay. So this is our generic equation for total response problems. Let me put a box around it. Now, one of the biggest questions that I get is how do I know whether or not to use the natural response equation, which is the thing we developed Wednesday, or the total response equation, which is this thing we've just developed. And there is an answer to that question. If there are sources left in at t is equal to infinity, you should be using this one. But you can use this one for all the circuits, and it'll still come out okay, because if it's a natural response problem, your analysis at infinity, everything's just going to go to 0. So it literally doesn't hurt you in any way, shape, or form to literally just use this one single equation for literally every and any transient analysis problem you will see in this class. You just might waste a little bit of time proving that things go to 0 at t is equal to infinity. How do you think using this equation is going to change our 4-step analysis process? There's just going to be one more step that says analyze the circuit at t is equal to infinity. That's it. So let's put this into practice. Do you want an RL circuit or an RC circuit? RL, okay. So let's say that we have a 3 amp current source . The switch is changing states at t is equal to 0. Let's put 5 ohm resistor here. Let's put a 10 ohm resistor here. Put a 20 ohm resistor here. Another 10 ohm resistor here. And then a 3 Henry inductance here. And let's say that I want to know my inductor current, IL, and this resistor voltage. Our first step will be to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, I'm going to label these positions A and B. So at t is equal to 0 minus, the switch is closed at position A, which means the 5 ohm resistor is being switched into the circuit or is in the circuit, and the 10 ohm resistor below it, one leg of it is left angling, so it's not going to influence the behavior at all. So I'm just not even going to bother drawing it because it's going to make it look awkward. Okay. So at t is equal to 0 minus, our circuit looks like this. We have a 3 amp source. We have a 5 ohm resistor. We have a 20 ohm resistor, a 10 ohm resistor. What does our inductor look like at t is equal to 0 minus? Short circuit. Thank you. Here is our inductor current, IL of t. Here's our voltage, excuse me, IL at 0 minus and VL at 0 minus, excuse me. That shouldn't be an L, that should be an R. My apologies. All right. Anybody care to venture a guess as to how we could solve for either of these quantities? Bradley. So not all of the 3 amps will flow through it because it still has to flow through some resistors and all that kind of stuff first, right? So what I mean by that is all 3 amps are going to flow through the 5 ohm resistor for sure. But then there's a path that has 20 ohms of resistance and there's a path that has 10 ohms of resistance. So it's obviously going to split. So based on that kind of looking at an analysis, seems fairly straightforward that we could apply the principles of current division to figure out how much splits and flows through the 10 ohm resistor, which is the current IL that we're looking for anyway, right? So anybody have any problems with using current division? All right, well, then somebody tell me how to do it. Sorry, what was that? It is if we're doing it the way that I told you not to do it. So let's do it the other way. 1 over 10. Exactly right. Thank you, Hayden. There's nothing wrong with what Carter suggested. I just don't particularly like that way because the resistor that you're not interested in is in the numerator, and I find that to be confusing. Okay. These two methods are equivalent, but this using the reciprocals works for any number of resistors in parallel. So to me, it has a greater utility, and that's the one that I use. So you're welcome to use it when you're doing your homework, your exam, whatever, but don't tell me you're using it in class. All right, so we should be easily able to see that this is 2 amps. So how do we get VR? Sorry, what was that? So the voltage drop across the 10 ohm resistor is the same thing as the voltage drop over the 20 ohm resistor because they're in parallel, right? So 2 amps times 10 ohms absolutely works. Or, as I believe Oren was suggesting, we could effectively do Kirchhoff's current law and figure out that there's 1 amp of current flowing down through the 20 ohm resistor, which will give us 20 volts also. So any way you slice it, the answer should be 20 volts. Technically, we could also say that it's 3 amps times 20 ohms in parallel with 10 ohms because we know that all 3 amps flows through that parallel combination of those resistors. That will also give us 20 volts. So literally 3 different ways we could solve for that voltage, all of relatively equal difficulty, all of them giving us the exact same result, 20 volts. Any questions, comments, concerns regarding our analysis at t is equal to 0 minus? Bradley. So let's make this 2 over 20, 2 over 20 like so. So we have 2/20 over 2/20 plus 1/20, which is the same as 2/20 over 3/20, or 2/3 times 3 is equal to 2. So calculator better. I don't know. Sorry, that wasn't meant to be insulting or anything, but you got to put it in right. Okay. Any other questions regarding this analysis? All right, let's move along to t is equal to 0 plus. I'm concerned here that we're actually not going to see any difference in the behavior of anything the whole time because of how I chose to do things here, actually, which is going to give us a little bit of a problem. So I'm trying to figure out, sorry, what I can do to fix it. So let me explain my reasoning here for why I think I've made an error in setting up this problem. So I'm switching between two different resistor values, but the amount of current that's flowing through that resistor is fixed, which means how it splits up is effectively fixed as well. Yeah, changing the current source to a voltage source would absolutely fix everything here. I'm just trying to see if there's something that I could change. Like if I change my 10 ohm resistor to a voltage source or something like that, if that would fix it so that we could keep the analysis that we did at t is equal to 0 minus. But I don't think it will, because that's just going to change the voltage. That's going to make the voltage drop over the current source change. Yeah, I apologize profusely, but I have to correct something at 0 minus so that this problem actually responds to the change. So I'm very sorry. Let's make this current source a voltage source, and then this will actually do something relatively interesting, at least to me. All right. Okay, so without me being a jackass and giving you a problem that doesn't actually involve a transient problem, now we have something that will. How would you go about determining the quantity IL at 0 minus or VR at 0 minus? Pardon? Okay, voltage division. I 100% agree with that assessment. Joel, do you remember how to do voltage division? Okay, so we could do mesh and get IL first and then use that to get VR. Okay, let's do that. That seems. How many, raise your hands if you would have even thought of voltage division. Me, Carter, and a handful of people. All right. Everybody else, I'm assuming, would have thrown mesh at it and saw what stuck. All right, well, I guess we'll throw mesh at it and see what sticks. I can't argue because I'm a jackass and setting these up poorly, so. Let's call this guy IA, this guy IB. So we don't have any super meshes or anything like that that we need to worry about, so we can pretty much just directly apply KVL around these loops. So it's going to look like negative 20 volts plus 5 ohms I1 plus 20 ohms IA minus IB is equal to 0, and then 20 ohms IB minus IA plus 10 ohms IA is equal to, excuse me, 10 ohms IB. Gosh, where's my head at right now? Is equal to 0. And then we can solve this system for IA and IB, where IB is simply IL at 0 minus that we're interested in. So solve it, Joel. Anybody verify those? Okay, that'll work for me. All right, so from that, IL is 1.14 amp. So VR will just be 10 IL. Or 11.4 volts. Using Ohm's law and the fact that those two resistors are in parallel, or appear to be in parallel at T is equal to 0 minus, I guess would be a better way of putting that. All right, anybody have any questions regarding our analysis at T is equal to 0 minus? I'm frustrated with myself because I just thought a way to fix the first problem. I could have just put a current source in there. All right, let's analyze the circuit at T is equal to 0 plus. Okay, so using voltage division, sure. No, not a problem at all. I feel pretty strongly that I multiplied 10 by 1.14 correctly. But using voltage division to get VR first, we would see that VR of 0 minus is 20 volts times 20 ohms times 10 ohms over 30 ohms divided by 5 ohms plus 20 ohms times 10 ohms over 30 ohms. So did you not remember that you need to look at the total series resistance? Yeah, so if you do this, go ahead and verify real quick that you get 11.4 volts just to make sure everybody's okay. 11.4 volts. Two different ways to get VR. And then once we knew VR, we could divide by 10 and get IL. So apparently we're just going to work this problem every way we can think of. That's okay. So circling back around, we analyze at T is equal to 0 plus now. So this is step 2. So at T is equal to 0 plus, we have our 20 volt source. Now the 10 ohm resistor is switched in here, if I'm not mistaken. $20 ohms goes here. Another 10 ohms goes here. What do we do with our inductor? Replace it with a current source having the same magnitude and direction as IL did. So that means we have a current source direction down with a value of 1.14 amps. And we're trying to find VR at 0 plus. So we know for sure IL at 0 plus is 1.14 amperes. Now we need to solve for VR. Any thoughts? Nodal, okay. Let's do nodal analysis. That's what I would go with too. Let's call this node VR. This bottom node ground. So that solving for VR gets us exactly what we're looking for. Everybody okay with that? So we could say that VR minus 20 volts over 10 ohms plus VR over 20 ohms plus 1.14 amps is equal to 0, where I've cheated here a little bit, okay? Normally, we would set the right-hand leg of that right 10 ohm resistor to be a particular nodal voltage. But I know for a fact that there's 1.14 amps flowing through it, so I just put that there, and that effectively let me eliminate a node and an equation from our analysis. So that we can take care of this guy, one equation, one unknown. Does anybody not understand why I can do that? Okay. Solve it. I literally don't know how to use the numerical solver on this calculator, so I can't. So, 5.7. Can anybody confirm that result? All right. Aiden, you get 5.7? All right. Okay. Anybody have any issue with our analysis at t is equal to 0 plus? All right. Now we'll analyze the circuit at t is equal to infinity. Oops, that went slightly too far. So at t is equal to infinity, the circuit is going to look exactly identical as it did at t is equal to 0 plus, but with one very important change. What does our inductor look like at t is equal to infinity? Pardon? What? Short circuit, yeah. So at t is equal to infinity, this represents DC steady state again. So this is a long time after the transient condition has died out and we've stabilized to a constant operating point, okay? So at t is equal to infinity, we should replace all of our inductors with short circuits and all of our capacitors with open circuits because we're back at DC steady state. So this circuit is incredibly similar to what we analyzed at t is equal to 0 minus, except that our 5 ohm resistor is now a 10 ohm resistor. So use whatever method you want to that we used back then, and then tell me what things should be. Joel.
So it's going to be the exact same if it's instead of going from one system to the other, it's closed. Same deal where infinity is going to be short.
Absolutely, yeah. So t at infinity, it just that represents a DC steady state condition. It has nothing to do with this circuit in particular. That's a general thing. So at t is, yeah, at infinity, doesn't matter if the switch is open or closed. We're at DC steady state, so all inductors look like short circuits and all capacitors look like open circuits. All right, so we have IL at infinity, VR at infinity. So either doing mesh analysis to solve for IL first or voltage division to solve for VR first. Somebody tell me what you get. Eight volts. Anybody else confirm that? Like David, I think, just gave me a thumbs up. All right. So this is how our circuit behaves at t is equal to infinity. Anybody have any questions? I guess I don't want to say regarding the analysis necessary since we didn't do any, but the analysis was so similar to what we did at t is equal to 0 minus that I feel like it's fairly straightforward. So let's go ahead and move along to step 4, which will be to determine our time constant. Because this is an RL circuit, tau will be L equivalent, which is just going to be the only inductor we have, divided by the equivalent resistance seen by the inductor. So L was 3 henries, if I remember correctly, from 15 minutes ago whenever we started this problem. In this one, REQ, we need to be careful about, okay? So we need to make sure that we are looking at the circuit during the transient condition. So that means the 10 ohm resistor is the one that switched in. The inductor gets taken out. Our voltage source gets turned off, and we look in through here. So what do we see? Orange? Don't have to give me a number, just tell me what's up. What does it look like? Yeah, so we see a 10 ohm resistor in series with a parallel combination of 20 and 10. So 10 plus 200 over 30 looks like 50 over 3 ohms. So from this, tau is equal to L divided by R. So that's 3 henries over 50/3 of an ohm. Looks like 9/50ths of a second if my flipping things around here worked. All right, so finally, we're at step 5, where we can plug stuff in. So as a reminder, our generic equation is now y of t is equal to y at 0 minus for t less than 0 minus y at 0 plus minus y at infinity, this whole quantity e to the minus t over tau plus y of infinity for t greater than or equal 0 plus. So IL of t will be 1.14 amps for t less than 0 minus. And we're going to have 1.14 minus 0.8. So 0.34 e to the minus 50 over 9 t plus 0.8 amps for t greater than or equal to 0 plus. And I'm just going to make a note real quick here. This is IL at 0 plus minus IL at infinity. And VR of t. Oh gosh, I don't remember what that value was. Let's look up here. 11.4 volts. And then we would have 5.7 minus 8. Negative 2.3 e to the negative 50 over 9 t plus 8 volts, t greater than or equal 0 plus. Go away. There, just as a reminder, this number right here is simply VR at 0 plus minus VR. So any questions regarding the process? If you follow those 5 steps and you do the circuit analysis at 0 minus, 0 plus, and infinity correctly, you're going to get the right answer every time. So we've got 30 minutes left, so take this time to start working on that in-class assignment. If you have any questions about anything, I would be happy to assist you.